Our next speaker is Jonathan Rudd, instead of Dennis Woods. The title of his talk is SAM, which is Sub-Audio Magnetics, which is High Resolution and Heat Exploration Case Studies. Jonathan graduated from Queen's University with Geological Engineering or Geophysics. He worked in both ground and airborne geophysics. The following companies: MPH Consulting, Digim, which is Fluoro CGG, airborne, Wallbridge Mining, Aeroquest Airborne. He is currently president of DIAS Geophysical, which offer fully distributed 2D and 3D resistivity and IP services.
Thanks, Bob, and thanks for this opportunity to chat about the SAM system. We had a long list of authors there, and we did that so that if somebody got stuck in China, we'd have options for who was going to present, and that's exactly what happened. Dennis is in China right now, so you're stuck with me. So I'm just going to provide an outline for the talk. We're going to introduce the SAM system, and then I'll give you some mineral exploration data examples, two of them, as shown there, one in Australia and one in Canada. And then we'll talk about a third application, which is in an oil and gas application in the oil sands in Alberta. So the SAM system, by way of introduction, is a sub-audio magnetic system. So sub-audio is what you can hear with your ear, so that's around 10 hertz, 10 hertz and lower. This proprietary electrical and EM technique was patented in 1991 by Cattach, its inventor and its developer. The transmitter is an active system, so the transmitter is a large grounded dipole, so similar to what you do with a gradient survey or a dipole survey. Or you can use an inductive loop transmitter. The waveform that we put through those is a 50% duty cycle, and as mentioned, the base frequency is anywhere between 4 and 8 hertz. The receiver is a total field magnetometer, so we measure the total field response as a magnetic measurement, and it's a measure with a high sensitivity cesium vapor magnetometer, and the trick with this technology is that it's measured very rapidly with that high sensitivity. And the receiver can be operated in either ground or airborne mode. The system has been active in Australia for over 2 decades, and most of that time the application was in environmental UXO application, so it's only recently been introduced in the mineral exploration industry. But it's demonstrated a good success in mapping conductivity variation in challenging environments, so where you've got conductive cover, a lot of that in the regoliths in Australia and salt pans. So more visually, these are the two transmitter, the two system modes. One is the inductive loop, so here we have a wire loop strung around the survey area. It could be offset depending on what sort of coupling you want. And the survey area is normally inside the loop, and then you survey lines across the survey area in your preferred direction. And that can be done either on the ground or using your own receiver platform. The second mode is galvanic, so you have 2 injection points, current injection points, joined by a wire. The survey area is in between those injection points. In the same manner, you can run your survey lines either on the ground or in the air. So this is an example of a typical transmitter electrode. You spend a bit of time ensuring you get good ground contact because you want to get as much current into the ground as you can. So normally dig a pit, put in some wire mesh or aluminum foil to get lots of surface area. And of course there's high voltages involved, so safety is an important factor. You can add ionized water to that to improve the contact. The transmitter it can be a conventional transmitter. These systems that GAP Geophysics in Australia have developed offer higher power, higher voltages than many conventional systems. So this is an example of one of those transmitters. This particular one is 70 kilowatts. They get up to 80 kilowatt systems, but of course, all with very robust safety systems. This one in particular can be operated remotely without any operator required on site or at the transmitter. The receiver systems, as I mentioned, either ground or air. The ground mode, you have your cesium vapor magnetometer, your recording device, and you have a GPS for location. So you normally will take two men walking and you're joined by a short cable. And in the air, it's a towed bird. In the bird, you've got a laser altimeter, you've got a magnetometer, you've got GPS, and it's towed at the typical of an airborne mag survey. So fairly lightweight equipment. So what are you measuring? You're measuring the total field. It's a scalar, so you're measuring a single amplitude of the total field. So that's the scalar you're measuring, and it's the addition of the Earth's field, which may be in this direction, and then the anomalous field, which could be in this direction. Normally, the Earth's field is much larger than the anomalous field, so we can do some math to simplify the processing of the data in this way. So let's look at some sample data. So here's a typical line of data across either ground or airborne. You can see that it varies temporally, so along the line, like that. And superimposed on that is is the induced waveform, the 50% to second waveform. So when you process the data, you can pull out your magnetic survey, so the total field, what you would normally collect in the mag survey. So just the smoothly varying magnetic field, Earth's magnetic field. And then you have your temporal component, which is the response to the active injection current or the transmitter input. And from these data, you're able to derive a number of data sets. Obviously your source, your Earth's field, mag, but also resistivity, EM, and induced polarization. So looking closer at the waveform here, we were able to derive resistivity data from the time period when the current is on. We're able to derive EM data from the early off time, and then IP data from the late off time. We're not normally able to extract all three data sets in one survey. You set up your survey to optimize two of those, resistivity and EM, or resistivity and IP. What's the processing workflow? You measure your total field mag data, and you spatially filter it to get your Earth's field out. Then you isolate your MMR signal. You have to remove the effects of the current that's flowing through the wire that's on the surface. And you also have to remove the effect in the galvanic source survey of the current that's going down into the Earth at the injection point. That's the vertical field. And then you have to consider that the anomaly shapes are dependent on the direction of the Earth's field in your local survey area. So the interpretation is not trivial, but it's achievable. So we produce an MMC, so it's called a Magnetometric Conductivity transform. It's much like a reduced to pole transform of magnetic data, which allows us to pull out the conductivity product from this data. So I'm going to move on to some examples. The first example is an example for gold exploration in Australia. It's courtesy of Gold Road Resources and targets Archean greenstone gold in Western Australia. The survey layout you can see here is three sets of grounded dipoles, from red, there we use to survey this portion of the survey, and likewise the green and the blue poles. This particular survey was done on foot. It could have equally been done using an airborne system, but I guess the economics dictated, or the speed required to use the ground acquisition. So these are the data results. On the left, we have the total field magnetic survey, as you get from any other mag survey. On the right, we have the Magnetometric Conductivity, so it's a derived parameter from the on-time data. And you can see relatively high resolution of the response across the survey area. So given a high resolution, you can take a vertical derivative of the conductivity, which is a bit challenging to think about, but you're really looking at trends. So there's a vertical derivative of the conductivity on the right. On the left will always be the magnetic data set verticals. And you can see a lot of detail in that survey area, individual conductive trends. You can see evidence of these structures that are coming across, and also evidence in that data set here. The next product is EM for this particular survey. So again, looking at the off-time data. I'm going to show you 3 channels of the EM data. This is the first channel, so it would include weakly conductive responses. And then later in time, so the more persistent conductors, the better conductors are going to show up and persist in the data set. And then the latest time channel, this is at 21.6 milliseconds, so a very strong late time response. So you can see you have some very strong conductors in the survey area. So this data set, so this data set provided high resolution reconnaissance style surveying for this particular area. They're in there to map a large area rapidly, and you're able to derive several parameters of the data set, mag, resistivity, EM. And if you set it up differently, you could have collected IP information as well. And the survey provides good depth penetration. You are looking at it as a plan map, in the same way as a gradient IP survey. You can't distinguish deep from shallow sources other than by the wavelength of the response. But a very quick, very inexpensive, and effective way of providing reconnaissance data for this type of survey. The second example is from Canada in Manitoba. It's a VMS country, volcanogenic massive sulfide, and in the Flin Flon camp. The survey was done under collaboration between GAP Geophysics, the owners of the technology, and Discovery International, a local geophysics company, and with the permission of Hudbay, who own the deposits and are currently mining it. It was surveyed in August of this past year, following another commercial honeycomb project in Alberta. So here we can see the general layout of the survey. The pink there is the transmitter loop, so it's an inductive loop. The black and blue lines are the actual survey lines. It was actually flown with the helicopter, so a towed Magbird helicopter survey. There is a road that extends into the mine site, which is an active mine site, and you can see there's a power line that accompanies it, and some other infrastructure as well. So about 90 line kilometers were flown, so it took maybe a couple hours to fly. The loop was already in place because it's being actively used, so very, very quick in-and-out survey, and we'll show you the results now. So the VMS deposit is the largest one in this Snow Lake camp. It's about 30 million tons, so a very large VMS deposit. You can see the reserves and resources there. There's 3 sort of distinct zones of alteration mineralization: zinc-rich, copper, gold-rich, and gold-rich. And the common factor in all of these is that there's a pyrrhotite matrix which runs through all of this mineralization. It makes it a very productive source. So a good EM target, of course. So the first derived product here is the total field magnetic data set. Maybe I should just mention that the survey was done at a 7.5 hertz base frequency, and we put out approximately 20 amps in the transmitter loop. So fairly standard transmitter power, not the higher power systems that the gap system provides. The total mag is shown here with reference to the transmitter loop, and then the yellow here is actually the outline of the surface projection of the outline of the known mineralization depth. The top of the mineralization is here, and it's at about 575 meter depth, and the bottom extends down to about 1 kilometer. So very deep target. The total mag doesn't show you really any evidence of that of the deposit, and we might expect it to. It's showing some trends in the Mira surface. These are relatively near vertical geologic features. So we're going to flip to the EM. I'm going to show you 16 channels of EM, lots of pages in your handout there. And I'm just going to flip through from channel 1 to the end. The most obvious effect in the early time channels is the effect of this power line. We can see that it's not noise generated by a 60 hertz signal, but likely a grounding of the power line and a ground bridge of some sort that's producing this response. And we'll see it diminish as time goes by. And you can see the response from the deposit down at 575 meters to a kilometer, building and persisting. Right to the last channel 16. And again, this channel 16 is at 28 milliseconds, which is not possible with other airborne systems. This is a combined ground and airborne, and that's one of the advantages. It provides for a low base frequency sensitivity to highly conductive targets. The response here is very comparable to what you'd get with the ground EM, a conventional ground EM survey. And the advantages of the HeliSAM system is that you don't have to cut or prepare your survey lines because you're flying the survey. It's a rapid acquisition, and then it's a B field measurement. It's a magnetometer that's measuring the response. It's a low base frequency, as I mentioned, 7.5 hertz, and a high signal to noise. The noise is low because it's a total field magnetometer. It's not prone to the vibration effects that coil systems have. And that high signal to noise produces a very strong depth penetration. So the third example is not a minerals example. I know there's a couple of people here that are in oil and gas. So this is from the Athabasca oil sands in Alberta. And it's a forward modeling study. We did do a survey, and I'll talk briefly about the survey, but I can't show you those results, unfortunately. So SAGD is steam-assisted gravity drainage. It's a method of extracting bitumen in situ in an oil sands environment. So to describe it, you drill these horizontal wells. You drill the horizontal wells, one on top and one below it. The top well, they inject steam, so hot water into it, and that steam emanates upward into the local chamber, I guess they call it, and melts the bitumen, or makes it more viscous, and it drops down, and then it's picked up in the lower well and pumped out. And so it's important to understand, a lot about what's going on in this environment, what's going on above it, because you need a cap rock to contain the steam, and you need to know exactly where your oil is in that section to maximize the recovery. The Clearwater Shale is a highly conductive unit which lies immediately above the reservoir rock, which is the McMurray sands. And the Clearwater Shale is a relatively thin layer, which occurs anywhere from surface to 500 or 600 meters. For SAGD, that clear water has to be about 150 meters before this method becomes viable. So mapping of the consistency of the clear water shale and the nature of the reservoir is critical to maximizing recovery in this environment. So how do electrical methods, electromagnetic methods, play in this environment? They rely on the difference between the resistivity of the bitumen, which tends to be more resistive, and the surrounding overlying sediments and sedimentary rocks. EM has been used extensively in the oil sands. Electrical resistivity tomography, which is a euphemism for 2D resistivity and IP, and then the airborne and ground EM methods. So time domain and frequency domain data is collected regularly in the environment. But at these SAG-D depths, 150 meters plus, it's really challenging to see through that conductive cap rock and understand what's going on in the more resistant reservoir rock. So these existing systems, the ERT and EM methods, lack the sensitivity and resolution to effectively map the clear water shale. So SAM, when we look at this, we consider that SAM might be able to provide some advantages. It is a high signal to noise system because low noise with a moving sensor here, and then the magnetostatic fields of the target anomalies are not attenuated by the conductive cover. So the experience in Australia with the regolith is the same as here. You get your signal down into the ground below your target. You energize your target, and then you're not actually having to get that signal back up through that conductive cover because you're measuring the magnetic field, not the electric field. So there's a significant depth penetration advantage with the SAM system. And that also applies to the airborne EM comparison. Another issue with the EM is that they tend to produce vortex currents. So a loop transmitter will produce a vortex current rather than a line current, which is what we're producing with the SAM galvanic source. And the fall off of a line current is less than a vortex current. So we decided to demonstrate through modeling that SAM can produce useful results for the SAG-D operators in a variety of scenarios. And obviously you have to demonstrate that your surface noise levels are sufficient to produce this value. So we used the modeling program EH3D. It's a frequency domain 3D finite code developed by UBC. It's currently still under consortium control, but this is to be released shortly, I think. So for simplicity, we forward modeled only the fundamental frequency, so at a 4 Hertz base frequency, we just modeled 4 Hertz. It came to about 62% of what you get if you modeled the full square waveform. But it provides a reasonable estimate and a conservative estimate of what the responses might be like. So here's a schematic model for the area. You can see here the Clearwater and Wabisca formations are in the top little section here. So these are conductive cap rock units. The McMurray extends from beneath the Wabisca all the way down to the Paleozoic. And the McMurray can be compromised, and the cap rock can be compromised by these channels. The channels can be clay, they can be sandy, they can be really anything. But they have a very large influence on the competency of the cap rock and also on the recovery in this environment. The bedrock topography is normally very easily mapped by seismic, so it's not of a concern. But seismic has difficulty in mapping a lot of these channels and these interfaces above. You can also get a lot of water occurring near the base here. And of course, the water replaces the bitumen and keep some as well. So here's a model example using Statoil's Leismer project. We can see here that the Clearwater cap rock is near surface here at about 250 meters. The McMurray extends from the bottom of that all the way down to the Paleozoic, but there's a water zone here at the bottom. So the actual SAG-D interval is fairly limited, from 190 to 220, about 30 meter section here. So you can see the wells that are coming down. This would be the steam injection well. This would be the extraction well below it. And so it's not trivial to understand where all these interfaces are. And this mud here is a channel, and it thieves away, and it actually pinches the reservoir rock out fairly effectively. So looking at the reservoir rock thickness here, here's a bitumen thickness map. You can see this section where it's pinched out the plan. So the view was that this could be a channel. And we'd be able to see that channel using the SAG-D method. So using the SAM method. So we modeled up the SAM system using some parameters given to us by Statoil, and we used the estimates of resistivity provided by Statoil. And you can see the Clearwater, quite a conductive unit. Well, it's also very conductive, very much more resistive, and then the limestone is also resistive. That's the discretization. And I have to speed up a little bit here, I'm running out of time. And so these are the results. So the modeling using a north-south dipole, random dipole, produced this response. And then the modeling using the east-west dipole produced this response in the data. So we can see that immediately that we are mapping that channel to varying degrees of accuracy in effect. If you put the two data sets together, if you combine the results, you can see that the shape of the modeled channel is quite pleasing and maps the shape and extent and the size of the channel quite well. The anomalous response is actually 150 picoteslas, you can see. So and this is assuming a fairly modest injection current amplitude. And with the noise levels at 15 picoteslas, you can see this is readily detected by the system. So SAM is a proven system, provides a multi-parameter data sets, which combines airborne efficiency with depth penetration, typical ground systems. It's demonstrated to be effective in Australia and Canada, and that it's also effective in the Athabasca oil sands environment. And acknowledging a variety of people here. And a couple of references. I'd like to thank you for your attention.
Thank you, Jonathan. We have time for one or maybe two quick questions.
Jonathan, great presentation. It's really interesting to see how this technology has developed over the last 15 years, where things are going. Just got a quick question regarding the IP. Are we able to acquire IP in all geological terrains, or are there certain areas where it's not appropriate?
Yeah, well, I think the experience is limited in the sense that it's been limited so far to the Australian environment. So we don't know how it will respond in all the environments. The key, obviously, is to be able to get enough current into the ground to make your signal level up. And that's going to be a challenge in some environments. Certainly, MIP and MMIP methods are of great interest where you sort of contact is an issue, like in Chile and
trying to understand something, so this is my bad, but I'm hoping you can explain it better. When you have the galvanic source, the results are strongly affected by that dipole orientation, this current temperature. So when you have the reduced source, the loop, you're going to get less channeling, sort of, it's less dependent on that orientation. So I suppose, do you have any examples, or can you tell me when you've done a galvanic source and a reduced source in the same block, if the results are similar or not?
Yeah, you'd probably have to talk to Mal about that. I haven't heard of any, to be honest. The inductive source is going to be used preferentially for, if EM is your target output, and the galvanic if IP is your target output. There are a couple of projects where we've modeled both to see what would be most effective, and there are certainly differences in strengths and weaknesses of the two approaches. And I think that speaks to the point.
All right, thank you, John.